Today, we're going to look at some basic graphs and transformations on those graphs. There's about 8 different transformations we can look at, so we're going to kind of skim through them so that this video doesn't take a real long time. And the idea is, suppose you have a basic function like f of x equals x squared, one of the ones we have memorized now. We know the graph looks like parabola. What happens if I want to graph something like f of x equals x squared plus 5? Well, if you don't know what it looks like right away, plot some points. Let's see, if x is 0, we get 0 plus 5, which is 5. Say right here. If x is 1, we get 1 squared 1 plus 5, which is 6. Say right here. At 2, we get 2 squared, which is 4 plus 5, 9. And it should be obvious at this point, it's going to go up like this. If you look at the other side of the graph, if you plug in -1, you get -1 squared, which is 1 plus 5, 6, which is right here. And again, if you plug in -2, you get -2 squared, 4 plus 5, 9, and you get that. And now it's pretty easy to see, it's just another parabola. And essentially, this one, the vertex is at 0, 0. This one is at 0, 5, which makes sense because of that plus 5 right there. And essentially what it tells us is, anytime we add outside of our function, the square is the original function, then we add 5 to it. Once we add outside of our function, we just shift our graph up. So, suppose we have f of x equals x squared minus 4. You could plot points for that if you want to. But again, logically, if adding a number outside of the function makes it go up, well then subtracting outside of the function will make it go down. And your graph will look like this. We shifted down, so this vertex will be at the point 0, -4, because we went down 4. As far as it goes with all of these transformations, basically, if you do something outside of your function, outside of your x squared, say, then it will affect your graph vertically. If you do something inside of your function, it will affect it horizontally. So, suppose we do something else. Say we get f of x equals x plus 2 squared. Here we see the difference. Before, we would square our x and then add 5. Here we're going to add 2 and then square it. So this is technically inside of the function. And to graph it, well, you can do the same thing, plot points. If you plug in -2, you get -2 plus 2, which is 0. And you get 0 squared, which is 0. If you plug in -1, you get 2 minus 1, which is 1 squared, and get 1. So at -1, you get 1. If you plug in 0, 0 plus 2 is 2, 2 squared is 4, and you get 4. And now again, it should be obvious, the graph will do that. If you plug in points on the other side, say if this is -2, plug in -3. -3 plus 2 is -1. -1 squared is +1. And again, now we shouldn't really have to plug in points. This should just be another parabola. It looks like that. And essentially, we did +2 on the inside of our function, and what did it do? It took our basic parabola and shifted it 2 to the left. Like I said, when you do something inside of the function, it affects it horizontally. The only trick here is that technically when you add, you go to the right. Normally when you add, you go to the right. But here when you add inside of a function, everything is reversed, so you go to the left. So if you have something like f of x equals x minus 6 squared, well, if adding 2 made me go 2 to the left, subtracting 6 will make me go 6 to the right. And this will be the point 6, 0. So now we basically have two different transformations. If we add or subtract outside of our function, it shifts it vertically. If we add or subtract inside of our function, it shifts it horizontally. Next, we can look at something like this. F of x equals 4x squared. And one key point to recognize, this 4 is outside of the function. When I plug in my x, I square it and then multiply by 4, which means it's outside of the square. We said earlier, if you do something outside of your function, it should affect it vertically. So graph it and see what you get. If we plug in 0, we get 0 squared, 0 times 4, which is 0. If we plug in 1, we get 1 squared, which is 1 times 4, 4. If we plug in 2, we get 2 squared, which is 4 times 4, 16. And then we're way up here, and it should be pretty obvious. It's just going to shoot up like that. Do the same thing on the other side, and we should get the same picture. If we plug in -1, -1 squared is 1. 1 times 4 is 4. That's the same, so we know the rest will work the same. And essentially, what did we do? Well, it got bigger faster. In math speak, since, like I said, this is outside of the function, we affect it vertically, we get what's called a vertical stretch. Basically, if you have something that looks like f of x equals a times x squared, then that results in a vertical stretch if a is greater than 1. 4 is greater than 1, so it stretches it. And by vertical stretch, we mean literally, we took our original parabola and just stretched it out vertically, which makes it look thinner. And we actually get what's called a vertical compression. If a is between 0 and 1. So if we did something like f of x equals 1/2 x squared. Well, if you think about it, I'm going to square x and then multiply it by 1/2, which will make it smaller, which will essentially make this get not as big as fast. So it'll have the effect of taking my parabola and pressing it down this way, which in math speak means it compresses it. I wrote this in terms of x squared because we're dealing with x squared. It will actually generalize to any function that we do. If f of x was x cubed, or the absolute value of x, if you multiply by something on the outside, if it's greater than 1, you get a vertical stretch. Your function will get thinner. If it's between 0 and 1, it's a vertical compression. Your function will get fatter, so to speak. But if we can multiply on the inside, then we can also do the same on the inside. So suppose we have f of x equals 4x squared. And the key point here is this time the 4 is inside of the square, which means we multiply by 4 first, and then we square it. So if we wanted to graph it, well, if we plug in 0, 4 times 0 is 0, 0 squared is 0, so we still get 0, 0. If we plug in 1, we get 4 times 1, which is 4, squared, 16. And we end up way up here at 16. If we plug in 2, we get 4 times 2, which is 8, then 8 squared is 64, and we're like up by the ceiling up there because I'm out of room. But we get the idea. It essentially shoots up like that really fast. Do the same on the other side. If you plug in -1, 4 times -1 is -4, -4 squared is positive 16. And we see it'll do the exact same. The trick here is that looks like a vertical stretch, and when you're graphing it, that's fine. In math terminology, that's not actually a vertical stretch, because we remember when you multiply or do anything on the inside of your function, you affect it horizontally, which means we can't call this a vertical stretch or compression because we have to use horizontal as far as the transformation goes. And the way it works is, same idea. If you have f of x, we'll say use the square again, and we do ax squared. Well, if a is greater than 1, which is what we have here, it makes it thinner. Or, if you think about it horizontally, it actually makes it compressed in this direction. So if a is greater than 1, you get a horizontal compression. And if a is between 0 and 1, we already recognized from what we did before, that will result in flattening my graph out, making it fatter. But horizontally, that means I grabbed it and I pulled it out this way to make it flatter. Which means now if a is between 0 and 1, that's actually a horizontal stretch. And you just have to keep the terminology straight in your head. Vertical stretches look the same as horizontal compressions, and vertical compressions look the same as horizontal stretches. Ultimately, the purpose of this class is not for you to learn the terminology, compression and stretch. Your goal is to be able to graph functions with all these transformations and to show me the transformations. Which means as long as you understand whether you're multiplying on the outside or the inside, it makes your graph look thinner, for lack of a better way of saying it, then you're fine. There are a couple more transformations we want to go over, but this video is rather long, so I'm going to end this here and we'll come back and do the rest of the transformations in another video.